Good morning, students. Myself, Dr. Eustace Russell, working as assistant professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. In the previous videos, we have completed Unit 1 for the subject called Robot Dynamics and Control, and we have seen some important derivation part as well as technically oriented concept also we covered so far. So in this, we will start with Unit 2 of Robot Dynamics and Control. We will see one by one of the upcoming slides. Syllabus of Unit 2, that is Robot Dynamics. So Unit 2, first unit is robot force models. This is Unit 2, that is generally expressions for kinetic and potential energy. Kinetic energy for an N-link robot, potential energy for an N-link robot, equations of motion, Lagrangian multiplier, Lagrangian equation, Hamilton equation, Hamilton vector field, Euler Lagrangian equation, state vector and equation formulation. These are the glimpse of our syllabus. Then kinetic and potential energy. Suppose an object consists of an continuum of particles and let rho denote the mass density. Mass of the object is expressed by m integral b rho x comma y comma z, that is dx dy dz, where b denotes the region of the three-dimensional space occupied by the body. The kinetic energy of the object is given by k equal to 1 by 2 integral vt xyz vxyz rho syz dx dy dz. Again we can write as half integral to v vt xyz v xyz dm, and dm is the infinitesimal mass of the particle located at the coordinates x, y, z. We find the coordinate vector of the center of mass as rc is equal to 1 by m integral to b r dm. Again continuation of the kinetic and potential energy, where r is the coordinate vector of a point on the body. Suppose we attached a coordinate frame rigidly to the center of mass with its origin at the center of mass. Velocity of any point on the body is obtained from v equal to vc plus omega r, which corresponds to the velocity with respect to an inertial frame expressed with respect to an inertial frame. So that is nothing but we wrote an expression called v equal to vc plus omega into r. Then r denote the rotational matrix that transforms free vectors from the moving frame to the inertia frame. Thus the velocity of a particle located at r expressed with respect to the moving frame equals, therefore rt vc plus omega into r is equal to rt vc plus rt omega into rt r. The kinetic energy is computed using any type of coordinate frame. It can be computed using the moving frame also. Now this slide, again we can express the vector cross product as a matrix multiplying a vector as follows: v equal to vc plus s omega r. S of omega is equal to 0 minus omega 3 omega 2 omega 3 0 minus omega 1 minus omega 2 omega 1 0. Then skew symmetric matrix, again one of the important concept we are introducing. Skew symmetric matrix means ST of omega is equal to minus S omega. Kinetic energy becomes, again we are having the lengthy expression. Kindly note down this. K equal to 1 by 2 integral to B Vc plus S of omega R, then Vc plus S omega into R dm. Again we can write this expression like this in this form. Finally you will be getting half m Vct Vc plus half integral to B RT St omega S omega R dm. It's a lengthy expression. So for any two vectors A and B, we can write as AT B equal to T gamma ABT. Using this equation again we can write as K equal to half M VCT VC plus half TR S omega N XT omega. Then N is the 3 into 3 matrix defined by integral S square dm, integral Sy dm, integral Sz dm, integral xy dm, integral y square dm, integral yz dm, integral sz dm, integral of yz dm, then integral of z square dm. Then after it can be further shown that k equal to half m vct vc plus half omega t I omega, where I is the 3 into 3 inertia matrix, that is again defined by, we have a matrix from that is I equal to integral of y square plus z square dm minus integral of xy dm minus integral of sz dm minus integral of xy dm integral of x square plus z square dm minus yz dm minus xz dm minus y integral of minus yz dm in integral of x square plus y square dm. Now consider a manipulator formed of n-links. Since the joint variables are indeed the generalized coordinates, it follows that for appropriate Jacobian matrices, that is JVCI, J omega I, we have that VCI equal to JVCI Q dot, omega I equal to RIT Q J omega I Q dot. Then RITQ takes care of the fact that the angular velocity must be expressed in the frame attached to the link. Suppose the mass of the link I is mi, and that the inertia matrix of link I evaluated through the coordinate frame parallel to frame I, but whose origin is at the center of mass equals I. Thus the overall kinetic energy of the manipulator equals. Again we can write this expression as k equal to half q dot t summation of I equal to 1 to n. Then inside the bracket we have a lengthy expression mij vci q j vci q plus j omega I q ri q ii rit q j omega I q, and outside the bracket it is q dot. In other ways you can write k equal to half q d q dot. D of q is the symmetric positive definite matrix that is in the general configuration dependent. Consider the potential energy term. In the case of rigid dynamics, the only source of potential energy is gravity. Hence the overall potential energy is given by integral to B g of t r dm equal to gt integral to B r dm equal to mgt rc. Then these are the various references I took for preparing this content. Derivation is somewhat a lengthy one. The terms are very new for you. Kindly go through it. You make use of these references. So thank you, students. We completed the first part of this unit 2, that is robot dynamics. The upcoming videos we will see with the next topics. Thank you, students.